And a happy Wednesday evening to you all. Here we are, originating from the studio for another ham radio class. This is a beginning ham radio class. We're probably about in the middle of the series, and we had a class last night for the amateur extra class, and the good news is we've got internet back here in South Carolina after the hurricane. The bad news is we discovered that it's not the same internet that we had before. I'm going to give you a little explanation about why this could be a rocky and bumpy class tonight, but we shall see. But before we get started, I just wanted to say that this is a beginning class. We work out of this book. If you take the laptop, Bruce, we work out of this book, the Ham Radio License Manual 5th edition from the American Radio Relay League. Normally I'd pick up the book and show it to you, except, Bruce, if you come back to me for a second, I loaned the book out to, of all people, my wife. By the way, this is my 3rd wedding anniversary, hubby, established 10/21 or 10/16/21. So, yeah, after Hurricane Helene, my wife said, hey, I think I need to have better communications possibilities. And so she's studying for her license unasked. Yay, Lisa! So we appreciate you, and I'll give you reports on that, but it just excites me a lot. So back to the laptop and Hurricane Helene. It caused devastation in South Carolina, North Carolina, areas of Tennessee. Then, of course, Milton came along afterwards. And we've been talking about radio and radio propagation. Well, last night we learned about something I like to call internet propagation. How everything on the internet is connected together. So I'm going to give you a little background behind the scenes. We have a Zoom classroom with students. Right now we have 12 students in the classroom. And we also stream live to YouTube. We've got 6 folks watching us on the live stream. And last night was a similar situation for the amateur extra class. Last night, however, we saw some things we'd never seen before. We saw this error message from YouTube, which says, your encoder is sending data faster than real time. We broke the space-time continuum last night. What? So that was YouTube. And then on Zoom, we got lost packet errors. And we were kind of glitchy. Things weren't smooth, and folks on Zoom, you might see that my resolution goes up and down. So all sorts of things are possible tonight. But this is what I discovered this afternoon when I was uploading a replacement video. We record here locally, and I was uploading it to YouTube. Normally, you see where the blue line is on the graph? That's what I consistently have from Spectrum, 20 megabit per second upload speeds. But you notice, and normally I'm able to saturate my upload right up to that speed limit and then no further. This is what's going on right now from my upload perspective. Only occasionally hitting that 20 megabit per second, usually much less, which is why, in the words of Betty Davis, fasten your seatbelts. It could be a bumpy night tonight. We could have the possibility of changes in the video resolution on Zoom. In fact, what I'm going to do now is I'm going to go ahead and spotlight me to make myself bigger for the folks in the Zoom classroom. So there may be changes in your video resolution. We could drop off of YouTube and then come back. Don't know exactly what's going to happen tonight, but let's get started, and hopefully we can make it through. We made it through last night, so fingers crossed. Tonight it's Chapter 5, and we're going to start with Section 5.1 on modulation. And first, just something real briefly, RF. RF is an abbreviation for radio frequency. And so RF means radio frequency signals of all types, from radio to television to telemetry to remote control to garage door openers to baby monitors. All of that is RF, radio frequency energy. And radio frequency energy doesn't really tell us anything or give us any advantages unless we can put information or convey information on a radio frequency carrier, and we do that through the process of modulation. Modulation is adding information to a radio wave. And different types of modulation serve different purposes. The most basic is Morse code here. When you turn the signal on and then turn it off in a pattern that folks at the other end can recognize, well, okay, then you can send text. And so that's Morse code. It got started with wire telegraphy, but then moved into wireless telegraphy. So that's one form of modulation, adding information to a radio wave. Now, Morse code is called continuous wave. It comes from the fact that previous modulation and signals were generated from sparks, from spark gap transmitters. So this was purer, this was much better. So continuous wave, CW is the abbreviation. So if you hear somebody talking about a CW signal, that's a Morse code signal. CW transmissions were said to go the farthest distance for the amount of power used. That has changed based on the power of computers. We'll talk more about that tonight. A CW transmitter emits energy on or about one frequency only, although it does have a bandwidth. We'll talk about that. Keying the transmitter on and off, the signal actually kind of widens out. Well, let's take a look. So here we are. Let me turn on my laser pointer. Oops. Find my mouse here. So here we are. So this is our radio frequency signal. We have an oscillator, a transmitter that we're transmitting on this one frequency. And by turning it on and off, we generate a signal that has energy here on this frequency and below that frequency and above that frequency. And the half power or minus 3 dB point, the half power point, that's where we measure the bandwidth in cycles. So here's a 150 hertz bandwidth, let's say. 75 hertz that way and 75 hertz that way. That's the bandwidth of a signal. CW signals, Morse code signals, are about 150 hertz wide. And in receiving this signal, what we like to do is to have our receive filters be about the same so that we don't get any of that extraneous noise and garbage. We just receive the signal that we're trying to receive. When you match the receive filters to the transmitted signal's bandwidth, you improve the signal to noise ratio. So that was the first, Morse code. And on ships, it was a godsend. SOS, think of the Titanic and lives saved. And then one lonely night, I think it was at Christmas time or New Year's, radio operators on board ships all of a sudden heard voices in the ether. Someone had figured out how to modulate the radio frequency carrier with a voice signal. And it started out very crudely, but worked its way out. And so amplitude modulation was the first voice transmission mode used with radio frequency carriers. And it has a modulating signal, which is of an audio frequency from like 30 to 3,000 hertz, for example. And it varies the amplitude of a radio frequency carrier in step with the modulating frequency. So you see the peak up here is the peak down here. That's an amplitude modulated radio frequency carrier. We're looking at it here, amplitude on the vertical scale and time on the horizontal scale. So this is what you might see if you had an oscilloscope connected to the output of a radio transmitter. You would see something very much like this. Now if we change and we go, here we're looking in what we call the time domain. If we change to look in something called the frequency domain, this is what we were looking at before. This is amplitude on the vertical scale and frequency on the horizontal scale. And so we have a lower sideband over here containing some information that comes from the audio in the case of amplitude modulation. And we have an upper sideband above the radio frequency carrier. And here's another way to look at it. Here's our audio signal, 300 to 3000 hertz. Here's that radio frequency carrier. Here's the lower sideband, and here's the upper sideband. And typically the bandwidth of, for communications purposes, not broadcast, but for communications purposes, the bandwidth is about 6 kilohertz for a voice signal amplitude modulated. And another look at it here with the radio frequency carrier there in the middle. We're here in the frequency domain looking at frequency on the horizontal scale. And the lower sideband is there to the left, and the upper sideband is to the right. Not to belabor a point, but here's in comparison with the baseband signal, the audio. Here's our AM signal with the lower sideband and the upper sideband. What would happen if we could eliminate the radio frequency carrier and eliminate one of the sidebands? Then we would have something known as single sideband modulation. So here's an upper sideband signal, and here's a lower sideband signal. And this was a technology, come back to me just for a second, Bruce, that was actually an issue for the United States in the Strategic Air Command. They needed to keep in touch with their long-range bombers, the B-36s and the B-52s that were around the world. And Collins Radio and Curtis LeMay at Strategic Air Command worked together to come up with this single sideband concept. The beauty of it is that the output section of a transmitter need only amplify the sideband. It doesn't have to amplify those other two, the carrier and the other sideband. And you can put all of the power where you want it, and signals on single sideband are said to go much farther than a conventional AM signal. And it proved true. They were able to maintain voice communications around the world using single sideband. So here's another look at it. In the laptop, we have the carrier and the lower sideband and the upper sideband. And if we can eliminate the carrier and upper sideband, then we're left with just the lower sideband. Or vice versa, we can be left with just the upper sideband. And the bandwidth of a single sideband signal is about half of that of an AM or amplitude modulated signal, about 3 kilohertz. That's the rule of thumb. On a lot of ham transceivers, you'll see adjustments, so for filters down to 2.8 or 2.7 or 2.6, even as low as 1.8 kilohertz wide. Those are useful in really high noise conditions, high interference conditions. When you're really trying to listen down into the noise, they can be helpful. But we talk about the bandwidth of a single sideband signal being around 3 kilohertz. So which sideband do you use? Theoretically, and technically, there's no reason why you couldn't use either. But by convention, in amateur radio, the dividing line is 9 megahertz. Below 9 megahertz, we typically use lower sideband. Above 9 megahertz for voice, we use upper sideband. And it goes back to the way some radios were built early on, a radio that could be used for 80 meters, for example, that could also be used for 20 meters. This made a lot of sense in the way the oscillators and stuff were set up. But now it's just by convention. There are some exceptions, and we'll talk about that. So we mentioned that we have the radio frequency carrier and single sideband, that we get rid of that, but we have a signal that has a definite bandwidth of energy. And we always want to keep in mind where that energy is. We always want to make sure that we watch out for where the band edges are. And so if you've got your color chart, I always like to show these. This is the American Radio Relay League amateur radio bands chart that tells you in the top frequency, the top end of the 20-meter band, for example, is 14.35 megahertz. Your energy, if you're going to be transmitting on upper sideband, we're above 9 megahertz, upper sideband on 20 meters, you can't have your radio dial set at 3.0 or 14.35, because your energy is 3 kilohertz above that. So the maximum frequency you can set your radio and be legal with your energy inside the band is 14.350 minus the 3 kilohertz, or 14.347. Overly complicated, but I just want you to be aware of the concept of the transmitted energy that you're transmitting has to be within the band. And if the band is divided up into Morse code portions or into voice portions, you have to stay within that mode restriction as well. So that was amplitude modulation, and single sideband is considered to be in the AM family. It is a form of amplitude modulation. Well, listen in your car to music, to broadcasting and whatnot. Most car radios have an AM band. They're trying to get rid of them in some of the cars. Also, though, people typically now listen on FM. FM is frequency modulation. So we talked about with a signal, a modulating signal, here's a sine wave, but we could say it's voice or whatever. For an AM signal, we change the amplitude in time with the voice. FM, you don't. FM transmits full power all the time. But what it does do is it changes the frequency slightly, lower in frequency or higher in frequency, in step with the modulating signal. So the fact that it's maximum power all the time, and the fact in receivers that we can put clippers top and bottom, it's immune to noise. Impulse noise, amplitude pulses don't affect it. That's why it's so clear. And they've worked it out so that the fidelity for broadcasting signals is much, much greater than the fidelity you can get from AM. So frequency modulation, and here's a closer look at that modulation scope. Now we're looking here in the time domain, so this is as if you had an oscilloscope and you were connecting it to the output of the transmitter, the AM transmitter there in the middle, and the FM transmitter on the bottom. So we've been talking about voice signals, communications signals, not broadcasting. And for FM voice communication signals, the bandwidth is typically 10 to 15 kilohertz. So remember, we started out with Morse code down 150 hertz. That's pretty darn narrow. We went to amplitude modulation, which was 6 kilohertz. Then we went to single sideband, which was 3 kilohertz wide. And now we're talking about FM between 10 and 15 kilohertz wide, wider than we've talked about so far. So interesting information to know, because you want to make sure that, in this case, you keep your transmissions within the band that you're going to be operating on. FM has another interesting characteristic. Only the strongest signal gets through. And it's not because of the transmitted signal, it's because of the receiver. Receiver demodulators will lock on to the stronger of two signals on the same frequency and pretty much eliminate the weaker signal. That's the way the demodulator works, and so you will only hear the strongest signal. I've been told this is not correct, but then I've read it is correct. That's the reason why in aircraft radios are amplitude or single sideband modulated, because with AM you can always hear other stations, even weaker stations. You may not hear them as clearly, but if there's two stations on the frequency at the same time, that's important for transportation. Whereas with FM, you're only going to hear the strongest of the two. That's called the capture effect. The demodulator in the receiver captures the strongest signal. All right, let's go back into time. Unfortunately, I'm old enough that this is not that long ago. I remember computers and computer modems like this acoustic coupler in the upper left that you'd stick a telephone instrument into it and you'd have 300 baud, 300 bits per second data, and I'd connect up to a local bulletin board system over the phone lines. Well, think of this era, And at the same time, hams were developing a wireless version of this, and it still exists today. It started as packet radio, and you used a computer or a dumb terminal even. Nobody knows what a dumb terminal is anymore, to talk to a box called a terminal node controller, or TNC. And the TNC would convert the digital data that you might be typing into audio tones, which were sent to a radio, typically an FM radio, that might transmit it out on VHF or UHF to another packet radio station where you could connect up and send messages back and forth, or send emails or messages to other people. We won't go deep into it, but it uses a protocol called X25 or AX25, amateur X25. It has various layers in the data with a preamble and cyclic redundancy checks for parity and things like that. But packet radio, remember, uses FM transmitters or phase modulated transmitters. Phase modulated, what's that? We talked about FM, changes the frequency of a signal. Well, there's also a way that you can generate a signal by changing the phase of the signal, and it kind of looks like FM. You can kind of look at it down there at the bottom. Here, the modulating signal is not a sine wave, it's a more kind of a sawtooth wave here, or triangle wave, and it's varying the frequency. But the thing is, with phase modulation, both the amplitude of the modulating signal and the frequency of the modulating signal vary the radio frequency carrier. And we'll go more into this in the general and extra class of why this is, but just need to know that FM and PM are kissing cousins. They're kind of the same, and any receiver that can receive FM can also receive PM signals as well. Now, phase modulation is not to be confused, we have a lot of terms, a lot of new stuff, with something called phase shift keying, or PSK. And this is a digital modulation process that conveys information by changing the phase of a carrier signal. So this doesn't look like anything we've seen before, but you can see that we're sending digital data here, ones and zeros, and you can see that the signal is changing as a sine wave, and then, it briefly goes back down again and starts again. This is changing the phase in concert with the ones and zeros. This is phase shift keying. Just want you to know about this. Another way to modulate the radio frequency carrier to convey information is frequency shift keying. Here you don't change anything on the radio frequency carrier other than its frequency. And it's in one state or another state, the mark state or the space state. And this is used for radio teletype. And is still a very popular mode, especially for contesting in amateur radio. You'll find a lot of folks doing radio teletype contesting. Back in the day, it used those old mechanical teleprinters that would go clackety, 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 clack, and smell like machine oil and whatnot. Now it's all done with computers, and it's really silent. So reviewing, Morse code goes the farthest for the power used. That's the old definition. We'll talk about FT8 here. Single sideband is the voice mode that goes the farthest. Think of Strategic Air Command and Curtis LeMay. They needed to have long-distance voice communications. There are some digital voice modes, but we don't talk much about it here in this class. FM has the clearest voice quality because of the way the receiver is immune to impulse noise. FM, PSK, FSK, and digital modes are used to transmit text files. And packet radio, that akin to bulletin board system, uses FM on VHF and UHF frequencies. They use the little handy talkies. The TNC connects up to little handy talkies. You can use them to send text. So this was near and dear to my heart. I spent many years as a broadcast engineer for both public broadcasting and commercial broadcasting before I joined Voice of America. So these old guys, I used to fix TVs as well back in the day. And amateurs can do television as well. And amateur fast scan television is the same as old analog TV that was phased out, and it was known as the NTSC system because it was developed by the National Television Systems Committee. NTSC, or as we broadcast engineers used to call it, never twice the same color. But it's used by amateurs in the UHF bands and above. TV uses amplitude modulation, believe it or not, with the part of the lower sideband is suppressed. So it's called a vestigial sideband transmission. A vestige of those lower sidebands still exists. And there's approximately a 6 megahertz bandwidth. 6 megahertz, that's really wide, which is why it's only used UHF and above. And this is the breakout of that 6 megahertz wide signal. You have a carrier frequency here. You have the upper sideband here with the luminance or black and white information. There might be a chroma or color subcarrier in there as well. There might be an audio subcarrier up here. And this is the vestige of the lower sideband. But this entire thing is 6 megahertz wide. So we talked about bandwidths. We talked about Morse code being 150 hertz, single sideband 3 kilohertz, amplitude modulation 6 kilohertz wide, FM 10 to 15 kilohertz. That might be important because we need to answer some questions. So let's see how we do. So which of the following is a form of amplitude modulation? You can go ahead and unmute and just let me know.
Charlie.
Charlie, single sideband, yes, is in the amplitude modulation family because it is derived from the AM signal. We didn't talk about how it's derived, that's in the general class. And what type of modulation is commonly used for VHF packet radio transmissions?
Alpha.
That you can use the little handy talkies. The little handy talkies are FM, full power all the time, or phase modulation, FM or PM. And which type of voice mode is often used for long distance contacts on the VHF and UHF bands? Voice mode, long distance.
Charlie.
Yeah, single sideband. Single sideband is the mode that goes the farthest. FM is full power all the time, but it's less easy to receive a weak signal on FM. So yeah, single sideband. And which type of modulation is commonly used for VHF and UHF voice repeaters? So you got your little handy talkie, you're going to talk into a repeater. So the repeaters all use frequency modulation. Those little HTs are all FM transmitters and receivers. And which of the following types of signal has the narrowest bandwidth?
Charlie?
Yes, Charlie. CW, Morse code, only about 150 hertz wide. And which sideband is normally used for 10-meter high frequency or VHF or UHF single sideband communications? So what I want you to think about is the 10-meter band or VHF or UHF, are they above 9 megahertz or are they below 9 megahertz? You can even go to your color chart and take a look at the 10-meter band. And you'd see that it's 28 megahertz. 10 meters is 28 megahertz. VHF is like 140 megahertz. They're all above 9 megahertz. And remember, I said that's the dividing line. Below 9 megahertz is lower sideband. Above 9 megahertz is upper sideband. You'll get it. So what is a characteristic of single sideband compared to FM?
Bravo.
Not Bravo.
Charlie.
It is Charlie. Actually, single sideband signals, remember, are amplitude modulated signals, so static or impulse noise will impact single sideband. So they are more susceptible to interference. But they have the narrower bandwidth. They're only 3 kilohertz wide, whereas FM is 10 to 15 kilohertz wide. So what is the approximate bandwidth of a typical single sideband voice signal? Were you listening?
Bravo.
Yeah, it's half of an AM, so it's 3 kilohertz. And what is the approximate bandwidth of a VHF repeater FM voice signal?
That's the one that's Charlie.
That's Charlie, indeed, between 10 and 15 kilohertz. And what is the approximate bandwidth of AM fast scan TV?
Bravo.
Yes, 6 megahertz wide. Very wide. So what is the approximate bandwidth required to transmit a CW signal?
B.
Yes, 150 hertz. And it varies with how fast you're sending the Morse code and how the adjustments are on your transmitter. So which of the following is a disadvantage of FM compared with single sideband?
Bravo.
Yes, with FM, remember, because of that capture effect, only one signal can be received at a time. So what is CW?
D.
D.
Okay.
It's another name for Morse code transmissions. So remember, these are the actual questions and the actual answers that you'll see on your 35-question multiple choice test that you'll be passing to get your ham radio license. Great. All right, we're moved on to section 5.2, transmitters and receivers. And I bring this in because it used to be that a lot of people came into amateur radio from the CB or citizens band world. Now a lot of people come in from family radio service radios, the little handy talkies, or GMRS radios. But it used to be that, you know, the old classic 23 or 40 channel CB, you know, you had a knob and it would go click, 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 and you had channels that you transmitted on. I'm on channel 9, or I'm on channel 16, or whatever else. Those corresponded to radio frequencies in the 27 megahertz band. But most people didn't even know that, or know what those frequencies were. In amateur radio, by contrast, we have something I call the big knob. This controls a variable frequency oscillator, and we can tune it, and we can transmit and receive at any frequency within a band that we desire. So there's no click, click, click. We actually, you know, tune the big knob to the frequency of interest for us. But we do share some commonality with citizens band radios. For example, some radios use squelch controls. Squelch is the thing that prevents a radio from just emitting a lot of white noise all the time. It makes the radio go silent. Only when a radio frequency carrier comes on frequency does the radio open up and allow you to hear what's going on. Common thing in citizens band radios, common thing in handy talkies. I've left my handy talkie downstairs, or I demonstrate it to you. and also on some high frequency transceivers. This is an Alinco HF transceiver I have in my truck, by the way, and it has a squelch control right there that I can adjust. So if I don't want to listen to the white noise all the time, but I'm waiting for somebody to call me on a particular frequency, I could, if I wanted to, turn the squelch control on. I have to say most hams don't use squelch, whether that's right or wrong, but it's a feature that's there that you can use. Now, we've been talking about something called carrier-operated squelch. That's when the radio will turn on when there's a radio frequency signal on frequency. But there are lots of other different kinds of squelch as well, and especially in mobile radios and in handy talkies. They make use of squelch of this other type. So they can use carrier-operated squelch, that works as well. But they can also use something called CTCSS, Continuous Tone Coded Squelch System. Motorola didn't like that name, so they called theirs PL tone, private line. Same thing. It's the exact same thing. There's also another thing called digital coded squelch. They have different names for Motorola and General Electric as well. But these are other signals that are added to the voice signal. In the case of CTCSS, they're sub-audible audio tones that are below 300 hertz. So most of the time you can't hear it, but they're transmitted along with your voice. What this little pilot signal that goes along with it does is that can be detected in the radio, and the radio can say, I'm only going to turn my squelch open, I'm only going to listen if that CTCSS tone is there as well. If that 91.5 hertz tone is there, whoop, then I'll open up. A lot of radio repeaters use CTCSS. You transmit on the input frequency to the repeater and nothing happens. Well, it may be because you haven't programmed the PL tone properly. And well, how do I know that, Gary? How do I know? Well, you can find the information in repeater directories. ARRL publishes a repeater directory every year. This is an old slide, 2016, wow. There's also apps for your phone. A nice free one is Repeater Book. If you've got a smartphone, you can look for the app Repeater Book. It's free, and when you have it running on your smartphone, it'll tell you all of the amateur radio repeaters near you. And it'll tell you all the information about them, their input and output frequencies, the PL tones that they might use, all of that information. And there's also repeaterbook.com for your laptops, so you can look them up that way. So,
Gary?
Yes.
Does that 300 hertz, does that add to your bandwidth?
The little subaudible tone, no, not appreciably, no. It's a very low-level tone, but the radio is sensitive enough to be able to receive it. But good question. And remember that an FM signal, we're talking about using this with FM, it's already 10 to 15 kilohertz wide, so what's a little bit more? It's not a big deal. So,
oh, right.
if you do want to receive a very weak FM signal, you always have to keep squelch in mind. And the thing is, if you want to receive a really weak signal, you almost all the time have to turn the squelch off. And most HTs, for example, have a button on the side you can push to turn off squelch, and then you might be able to hear a weak signal. So how to achieve weak signal reception on FM? Well, you turn off squelch. That's one thing you have to do. So we mentioned before that modulation is the process of putting information on a radio carrier. And there's all sorts of different input devices for your radio to do this. And we talked about Morse code with keys. You can also have paddles, also different types. We'll see another one here. Microphones for voice, and keyboards for data, and even they have Morse code keyboards for sending Morse code. Morse code is alive and well, and it's no longer a requirement to get your amateur radio license, yet it is even more popular now than it was before, believe it or not. And there are places where you can learn Morse code quite easily. We recommend the Long Island CW Club. great organization that can get you started if you'd like to learn Morse code. There's also another organization called CW Ops that they have online training. So you don't have to even leave your home, and you can gain proficiency in Morse code, and then you can listen on the ham bands and you know, use what you've learned in the classes, like learning a language. Now, if you want to send Morse code, you can use one of those keyboards, or you can use a straight key. A lot of people, though, will use iambic paddles right here, whereas you push one paddle, it sends a dit, a short, and the other paddle sends a da, the longer tone. If you squeeze them, that it alternates between dits and das. All of that is done by the paddle and an electronic keyer. This is an outboard electronic keyer for a radio. Most radios nowadays have them built in. You don't have to get an outboard unit, but an electronic keyer, whether it's inside the radio or external, they're used to enable sending Morse code from a paddle. All right, this isn't on the test anymore, but I always like to point it out. Microphone connectors for amateur radio transceivers nowadays. This is a standard 8-pin connector there on the left, and the corresponding plug. 8-pin connectors are being used, or have been used, by Yaesu and ICOM and Kenwood. But here's the secret: they're not compatible. The pinouts are different. So an ICOM microphone will not work on a Kenwood radio. So you always have to keep that in mind. If you want to use a headset, for example, then you typically will buy adapters like this, or like we have here on the next page, where you can adapt a microphone, a standard XLR connection, for example, to an 8-pin connection. Or Bob Heil's Sound makes a bunch of these adapters here, so you can use headsets with various radios and the 8-pin connection here. But keep that in mind, that if you have a Kenwood radio and you've got an ICOM microphone, you might need to trace out what the wires go to, and you might have to do some soldering and rearrange things, or call a friend and say, help. Some work might be involved, but just keep that in mind. When you're transmitting voice, and this is what I like to do, in fact, we've got a contest coming up in another week, the biggest annual single sideband contest, the CQ Worldwide. And so your voice quality is important, both in amplitude and in clarity, and you want to make sure that your microphone gain, for example, is set properly. Too little, you're never going to be heard. Remember, it's amplitude modulation, single sideband for long distance. Too much, you're going to get distortion and clipping. It's going to make the signal not right. So you want to make sure your signal levels are set properly, and your voice equalization is set properly. And that's what a lot of the knobs on radios are all about. If you look at ham radio transceivers, the typical ones have lots of buttons and knobs. I love it. Some people are intimidated by it, but I enjoy learning about, what does this do? Well, what does that do? And it's a mastery. You're learning your instrument, for example. You're learning how to use your radio more efficiently. And we talked about the big knob. That's the variable frequency oscillator. That's one of the controls. There's also probably a mode selector switch there, because HF transceivers are typically multi-mode radios that can send and receive AM, single sideband, Morse code, FM, radio teletype, all sorts of different things. The radio's probably got a bunch of memories where you can hold frequencies and mode information. It's a quick way, if you've got a net you like to listen to, or a frequency that you like to listen to in the morning, for example. I listen on the 80-meter band 3950 every morning to the group of the guys there. I never participate, but I listen every day just to see what's going on. And you can put that into memory, and boom, then you always get right back to there. HF transceivers are multi-band. That color chart, talked about the high frequency bands from 160 meters up to 6 meters. That's the typical arrangement for high frequency transceivers. They'll work all of those bands. They're multi-band radios. Tuning, we mentioned you can put a frequency in memory. That's one way. You can adjust the big knob. That's another way. A lot of radios also will have keypad entry where you can actually plug in, like in a calculator, punch in the numbers of the frequency, hit enter, and boom, you'll be on frequency. So those are all different ways you can change the frequency of your radio. If you have a receiver, there are two basic terms that you need to know about. Sensitivity, that's a radio's ability to detect a weak signal. How sensitive is it? And selectivity, that's the ability of the radio to hear what you want to hear and eliminate everything else. So sensitivity, weak signals. Selectivity, eliminating interference. Those are two characteristics that good radio receivers have. Receivers have all sorts of different controls. They have an AF control. I love this. Audio frequency. It's a volume control. Why do you call it A? Okay, but on transceivers you'll see it AF. Older radios don't do this anymore, but had an IF gain control, an intermediate frequency gain control, but you'll see it. They have IF passband tuning, both old radios and new. It allows you to modify the bandwidth of the receiving system to match the modulated signal, because remember we said that's when you get the best signal to noise ratio. IF filters, also you'll be selecting a filter that is the appropriate bandwidth according to the mode. So for Morse code, you'd want one around 150 hertz wide, or maybe 500 hertz is a more typical one. For single sideband, 3 kilohertz, or maybe 2.8 kilohertz, something like that. An RF control, an RF gain control, is a radio frequency gain control that actually controls the input section of the radio, how sensitive or how less sensitive it is, which can sometimes help you reduce noise as well. Some people actually find it's better to tune with the or to listen with the RF gain control than with the AF gain. There are notch filters. If you have an interfering signal nearby, you can eliminate it with this notch. And attenuators reduce interference from strong signals that might be nearby. And when we're selecting the receiver filter, remember we want to match the transmitted bandwidth for the best reception, and we do that because we get the best signal to noise ratio. Now another feature of radios, old and new, is automatic gain control. And if you go to the ham radio clubs and you find the older ham radio operators, especially the old Morse code operators, this is kind of what they look like, because they've been listening for years and years and years with headphones on with the automatic gain control turned off. That's not a good idea. You're listening for a weak signal and then a very strong signal comes up on frequency, you can blast your ears. So use automatic gain control. What it is designed to quickly moderate a signal if you have a really strong signal coming on frequency. It keeps audio at a constant level. So AGC is a good thing. We have the big knob where you can change your transmit and receive frequencies, but sometimes you just want to change the receive frequency. If I'm listening on 3950 to the guys and somebody's slightly off frequency, well, I can use my receiver incremental tuning. It's a kind of a fine tuning just for reception to allow me to clarify or to hear a single sideband voice signal better. Sometimes it's called a clarifier on some radios. That's receiver incremental tuning, or RIT. A lot of controls on these radios. We're just going over them, just kind of reviewing what some of them are all about. And in this case, it can be used to make a single sideband voice signal sound normal. Single sideband can be very difficult to tune. It's kind of fiddly. So on radio receivers, you'll find this. It's an S meter, it stands for signal strength meter, and it's telling you on a meter movement how strong the signals are that are coming in that you're trying to receive. And 1 S unit, that's the, so here we have S9 on the meter, here's S8, here's S7. So to go from S7 to S8, this is 1 S unit. And we say that's about a 6 dB difference. That's the standard, or about 4 times. So for a transmitter that's transmitting on 100 watts, for example, and they want to improve their signal, to get from S7 to S8, they don't have to transmit another 100 watts. No, they have to transmit 400 watts, 6 dB, in order to get 1 S unit difference. So that's what this is all about. It's a logarithmic relationship. And when you get above S9, then it is actually measured in decibels, plus 10, plus 30, plus 60. But 1 S unit difference typically is a 6 dB or 4 times difference. Some radios it's not strictly calibrated that way, but that's the standard. Now we mentioned that single sideband is part of the amplitude modulation family, and sometimes impulse noise from electric fences, or if you're mobile in the car from spark wires, things like that, will have an impulse noise that control on your radio might be able to eliminate. It's called the noise blanker. And what it does is it squelches the audio during sensed noise peaks. So you see the noise pulse up here on the top coming in, and it's squelched out very briefly so that in the end you don't hear it on the audio output. That's a noise blanker. And you can have different styles of that, and sometimes they're variable. Always a handy thing to have. I used to own one of these. You don't need them much anymore, but a radio frequency preamplifier. On the old vacuum tube radios, especially the higher frequency bands, 10 meters for example, they got kind of deaf. They would, their sensitivity was not good. They couldn't hear the weak signals. And what you'd have to do is use this ahead of the radio, and this would preamplify signals coming from your antenna before it got to your radio receiver so that the radio could hear them better. That's a radio frequency preamplifier, and it installs between an antenna and a receiver. And some of these were also designed for use with transceivers. They would sense when you transmit, and they bypass their amplification and go straight through when you transmit. So that's, you don't damage the preamplifier in that case. But this is an RF preamplifier. Preamplifiers go with receivers. Some more controls. We talked about mic gain, that you want it to be just right. Speech processors, compression. Compression can help raise the average signal level of a single sideband voice signal, for example, which will make it more audible a long distance away. Some radios have RF power level controls. The reason you might want this, a 100-watt radio, you think, well, I'm going to transmit at 100 watts all the time. That's great until you get into the idea of, well, I think I want to go higher than that. Then you need something called a radio frequency power amplifier. So this is one from Elecraft, the KPA 500, the one I just bought back from Doug. Thanks, Doug. I have one downstairs in the workshop. I built this one, actually. It's a 500-watt amplifier, linear amplifier. See, I almost made a mistake there. Not preamplifier. Preamplifier goes with receivers. Linear amplifiers, or power amplifiers, go with transmitters. And it increases transmit power. So this 500-watt unit, for 30 watts in, will give you about 500 watts out. That's where the RF level or power control on your radio, you might need to turn it down to 30 watts before you run it into a power amplifier like this in order to get 500 watts out. A little less gives you a little more. That's kind of cool. And they make these for high frequency. This is a multi-band linear amplifier that has bandpass filters that switch from band to band from 160 meters up through 6 meters. They also make these for VHF and UHF. They don't typically look like this, although Beko in Germany makes some that look like this, but typically they'll be bricks or things like this with fins on them for cooling. They're solid state devices, and they're powered by 12 volts or 13.8 volts DC. The thing to know about these VHF, UHF power amplifiers is that they may, on the front panel here, they typically will have a switch that changes the mode of the amplifier. You want a linear amplifier, one that amplifies exactly what's coming in a linear fashion for single sideband, amplitude modulated signals. For FM or Morse code, however, the amplitude doesn't matter because that always is going to be pretty much constant, so you can go to a Class C mode and get a little bit higher output. So that's what the mode switch is here on some of these VHF and UHF power amplifiers. So RF power, you'll see ratings. So the amateur radio standards in the United States are that the maximum output power that amateurs can transmit is 1,500 watts peak envelope power. What does that mean? Well, peak envelope power is the kind of power rating we use when we're talking about amplitude modulated signals, AM and single sideband. Continuous power is what we talk about with Morse code, FM, or radio teletype. It's a different measurement, way to measure RF power. At full output power for FM, for example, is the same as 100% modulation for PEP. So the same amplifier can be used for either. And here we have the block diagram of how you would have a transceiver, a linear amplifier, possibly a low-pass filter, a measurement bridge for standing wave ratio that we learned about last time around, an antenna tuner, and your antenna. This is the block diagram of transmitters from a transceiver to antenna. So the amplifier here is an important part of a lot of ham stations. The problem is, remember we said that RF gain control? If you send too much power to the linear amplifier, the amplifier it doesn't have infinite energy. It runs out of energy and it clips the top and bottom of the radio frequency carrier waveform. Let's look at it here. The top section is missing. And this causes distortion, this causes spurious harmonic output, bad things. So that's called overdriving an amplifier. And this is what it looks like in the time domain. You actually can, on an oscilloscope, see it clip the signal. In the frequency domain, you actually see the signal that you want, but then you see harmonic and spurious signals that you don't want. That's caused by overdriving a radio frequency amplifier. It can happen at HF. It can also happen at VHF and UHF with those brick amplifiers. Dummy loads are test antennas. They're antennas that don't radiate a signal. One of the most famous was the Heathkit Cantenna, which had a non-inductive 50 ohm resistor mounted in a paint can full of mineral oil to dissipate the heat. You could run your output of your transmitter or your amplifier into one of these dummy loads and do your testing without radiating a signal. So this is for a high power 1,000 watt signal, for example. Here might be for about a 10 watt signal. Here maybe for a 5 watt signal from an HT. But these are all test antennas, also known as dummy loads that allow you to do testing without radiating a signal. Good thing to have. All right. You can spend hours on this subject, computers and ham radio. There are just so many uses: logging contacts, sending and receiving Morse code or radio teletype. You can actually use software-defined radios that are either local to your station or on the other side of the world over the internet. You can use it with your antenna analyzer to display graphs and charts. You can operate your station remotely over the internet, and you can use digital modes such as FT8 that we're going to talk about. And you use computer sound cards in this case because you want to convert audio into information that the computer can use, and you want to use the computer to take information in it and send it out as audio tones. And earlier radios, HF and VHF, UHF, you had to buy a radio interface, like the Signal Link on the left, or the other one from West Mountain Radio on the right, that would interface your computer via USB to your radio via audio lines, audio coming from the radio to the computer, or audio coming from the computer to the radio, and something to transmit, to activate transmit on the radio. Those three signals are all necessary before you can use modes like FT8 or even radio teletype through audio frequency shift keying. You need an interface like this, unless you have a more modern radio. So here's the 7300. ICOM has sold over 100,000 of these radios. It is probably the most common, most popular new radio still being sold out there. And it has on the back of it a USB jack. It has an interface built in. So all of those three signals, the audio coming from the computer, the audio going to the computer, and the push-to-talk line for the transceiver, all of that is handled by one USB connection and software that runs on your computer. So modern radios will all have, whether from Yaesu, Kenwood, ICOM, Flex, what have you, will have an interface built in to do this. And okay, here I've got my HF radio. I can transmit all the way up to the 6-meter band, but I want to transmit up on the 2-meter band or the 70-centimeter band, and I want to be able to receive signals. Well, you could buy another radio, or you could get one of these. This is from Elecraft as well, the same people that had that power amplifier. This is known as a transverter. It converts both transmit and receive signals to a different band. So you could get a 2-meter transverter and operate it in conjunction with your HF radio, and away you go. You're on the 2-meter band, receiving and transmitting. That's a transverter, does both receiving and transmitting. A lot of stuff covered there. Let's see how much we can remember. Let's answer some questions. So why should you not set your transmit frequency to be exactly at the edge of an amateur band or sub-band?
Delta.
You think? Let's see. To allow for calibration error in the frequency display. Yeah, okay, there. So the modulation sidebands do not extend beyond the band edge. Yeah, we talked about that. To allow for transmitter frequency. Yes! All of those choices are correct. And what would cause your FM transmission audio to be distorted on voice peaks?
Charlie.
Yeah, out of the things that they give you here, if you talk too loudly into the microphone, you can clip the voice peaks, so yes. So what is the purpose of a squelch function?
Bravo.
Bravo is correct. That's to mute the receiver audio when a signal is not present. And what is an electronic keyer?
Charlie.
Yes, it's a device that assists in the manual sending of Morse code using one of those iambic paddles, for example. And what is the effect of excessive microphone gain on single sideband transmissions? Remember, you want it to be just right. because if it's turned up too high, your audio is going to be distorted, number one, and you're probably going to pick up a lot of room noise, fans or other thing going on in the background. So you want to make sure that your transmit gain control or microphone gain is set properly. And which of the following can be used to enter a transceiver's operating frequency?
Delta.
No, not delta.
Alpha. Alpha.
Alpha. A keypad
okay.
or the big knob. So how is squelch adjusted so that a weak FM signal can be heard?
Alpha.
I don't like the answer. The answer should be you turn it off. Set the squelch threshold so that the receiver output audio is on all the time. You're turning the squelch off. So what is the way to enable quick access to a favorite frequency or channel on your transceiver?
Bravo.
Yep, store it in a memory channel. And which of the following controls could be used if the voice pitch of a single sideband signal returning your CQ call seems to be too high or too low?
Delta.
Yeah, the receiver incremental tuning, also known as a clarifier, you can fine-tune the receive. And what is the advantage of having multiple receive bandwidth choices on a multi-mode transceiver?
Alpha.
No.
Mhm. Oh, Bravo.
Yes. Permits noise or interference reduction by selecting a bandwidth matching the mode. So you want a narrow filter for CW or a wider filter for AM or single sideband, for example. All right, which of the following receiver filter bandwidths provides the best signal to noise ratio for single sideband reception out of these choices?
Charlie.
Charlie is correct. Single sideband is about 3 kilohertz wide typically, depending on the receiver or the transceiver setup, but you don't want it wider because you're just picking up excess noise. All right, what is the result of tuning an FM receiver above or below a signal's frequency? If you misprogram your radio and you don't quite get on the receiver's input frequency,
Delta.
yeah,
Delta.
it's gonna sound distorted. People will say, "Hey, you're off frequency." So, which term describes the ability of a receiver to detect the presence of a signal?
That's Bravo.
Yeah, how well can it hear? How sensitive is it? And which term describes the ability of a receiver to discriminate between multiple signals?
Charlie.
Yes, take what you like and leave the rest, selectivity. And what device converts the RF input and output of a transceiver to another band?
Charlie.
Yep, that's a transverter. Transmit, converter, transverter. And what is the function of a transceiver's PTT input? I didn't specifically say, but I think you can puzzle it out.
Bravo.
Yeah, when you ground out that circuit, that line, you go into transmit. So it switches the transceiver from receive to transmit when it's grounded. And what is the function of the SSB CWFM switch on a VHF power amplifier?
Bravo?
Yes, it's a mode selector switch. You want to have it in one position for single sideband amplification, and in another position if you want to do Morse code. It puts the amplifier, it biases the amplifier in a different way. We won't go into details. In general class we do that. So what device increases the transmitted output power from a transceiver?
Bravo?
Yes, an RF power amplifier. You're increasing the output power, so it's an RF power amplifier, also known as a linear amplifier. And where is an RF preamplifier installed? Think of those old deaf radio receivers.
Charlie?
No? An RF preamplifier
I'm sorry.
is used for
Yeah.
receiving, yes, so it's between the antenna and the receiver. Yeah. And what can you do if you're told your FM handheld or mobile transceiver is over-deviating? The modulation is too loud.
D?
D, talk farther away from the microphone. It's as simple as that. So what is the primary purpose of a dummy load?
Alpha?
Alpha, to prevent transmitting signals over the air when making tests. And what does a dummy load consist of?
Bravo.
Yeah, you got to have some way to take the heat away, because the load resistor is going to take the RF power and turn it into heat. It may be in a mineral oil bath or something like that, or maybe fins on a metal heat sink. So it's a non-inductive resistor because you want it just to be a pure resistance, so it generates the heat. We have gone through two major sections in the book, and I'm very proud of you. It still may be confusing, but don't worry about it. That's completely normal. And now you have earned a 5-minute intermission. So let's take 5 minutes, get up and move around, get out of your chair, get something to drink, and come on back. And then we have two shorter sections to finish this up. right, you're doing great. So proud of you. Some of the hardest stuff we covered tonight already. So we got a couple more shorter sections, and then we'll get you home. Oh wait, you're already home. Let's start with the section 5.3, digital communications. And digital communications used to mean something like this. Remember I talked about radio teletype being those old mechanical devices, clackety clackety with lots of machine oil smells and things like that. Well, then they went to terminal devices like this. You could send and receive radio teletype and even Morse code using one of these devices. And then they went to software. And on personal computers now you can run software that can send and receive all sorts of different digital modes. And using an interface to your radio, you can send and receive. Packet radio, remember we talked about that before. That was probably the first amateur radio true digital mode, dating from the 70s. I first did packet radio back in the 1980s, back when I was up in Michigan. Again, remember it was likened to the old bulletin board systems. It was VHF and above. It used a terminal node controller box connected between your computer and a handheld radio usually. It used the AX25 protocol with those various parts that I showed you earlier, the header and the checksum and the data and an automatic request to resend. If a packet didn't make it from one station to another and the TNC at the far end could say, hey, wait a minute, I didn't get that right, parity isn't right, it would send a request back saying, send it again. That's packet radio, automatic repeat request. Oh, I didn't get it, send it again. Well, packet radio evolved into something we use today known as APRS, or the Automatic Packet Reporting System. I sometimes call it the Automatic Position Reporting System. It integrates a GPS receiver into the mix, and the GPS receiver has your latitude and longitude that it inputs into the data that is contained in the packets. And you can also transmit very short text messages for tactical use along with the position data. And if you go to this website, aprs.fi, and you can move the map around to your location, you can actually see ham radio operators on the move in your area with radios in their vehicles that have the APRS ability turned on. And uses digipeaters to send this information out to gateway stations, and the gateway stations put it out on the internet. It's collated and put together on this website. So aprs.fi. A lot of radios now come with not only the APRS TNC built in, but also a GPS receiver as well. So it's all integrated in one box. Kind of a nice feature. Gary, I like to send email. I like to, receive email. Can I do email over ham radio? Yes, using something called WinLink, Windows Messaging over Radio. There are, as I mentioned before, gateway stations, just like APRS, gateway stations that interconnect the radio universe to the internet universe. And so by connecting on predetermined frequencies to a gateway station, you can send and receive email on high frequencies over very long distances, and then also on VHF and UHF. And there's the URL there for winlink.org. You can find out more information. So that's a digital mode that is used on radio, amateur radio. Now, there are a bunch of others. Data modes on the high frequency bands are limited though to 300 baud as far as their symbol rate. Remember, that's that old telephone modem speed. Here's some factoids. Radio teletype uses not even ASCII's 8-bit code, but it uses a much older Baudot code developed by a Frenchman with 5 bits. So radio teletype is 5 bits. There's something called PACTOR. which uses frequency shift keying along with an automatic repeat request like packet radio. And this is great for sending text messages and data files. And PACTOR is being used a lot in disaster areas. Puerto Rico, when the hurricane came through there. I imagine now even with the Milton down in Florida and Helene up in North Carolina, that PACTOR is being used. And they have various flavors, 1 through 4, of PACTOR to send important data related to emergency and disaster relief. We talked about WinLink. Another acronym for it is WinMore, WinLink messaging over radio. PSK31 used to be a very, very popular keyboard-to-keyboard mode, much like radio teletype, using phase shift keying. And then one day, well, it didn't disappear, but it might have because this came along. And we were teaching classes at the time that FT8 was introduced to the amateur radio community. And to say that it took off is an understatement. FT for Frankie and Taylor, 8 multitones. Well, anyway, Joe Taylor is the guy up in the upper right-hand corner. He's one of the guys that developed the FT8 mode, and it was derived from a mode that he developed earlier, FT65, for Earth-Moon-Earth communications. And you can run FT8 using software, WSJTX software. There's the URL up there. It's free. And JT65, as I mentioned, was used for Earth, Moon, Earth. The whole point of this software is that it uses computer power and time instead of big hardware and high power. It allows the average amateur radio operator to do impossible things like send or receive signals from the moon. Well, FT8 also uses this, and so with a very low power station, 100-watt station, you can work around the world even on bands that are dead, that you can't hear any signals there. The computer can hear signals that you can't hear with your ears. So Steve Frank and Joe Taylor were the primary. There was a Brit also in there, developer of the software. 8 is for the 8 frequency shift keying format that the signal uses. It occupies just a 50 hertz bandwidth. So remember I said that CW is the mode that goes the furthest? Well, not anymore. FT8 does. It's a weak signal mode that can hear barely audible or even inaudible signals. And back on the other side of the 11-year sunspot cycle, when band conditions were just horrible, you could hardly get a voice transmission through because voice requires about 20 dB more signal at least than Morse code or FT8. FT8 works great with dead bands, so to speak, and so it became very popular. Now, popular with a group of hams, unpopular, we have our curmudgeons. The old-timers. The old-timers objected to FT8. It's a contact. It's not a conversation. Because the computer, all it does is it sends your call sign, it sends a signal report, it sends a Maidenhead, your location, the EM84 or whatever. That's it. You can't say hi. You can't say, how's the wife? You can't talk about politics, religion, or anything. You just make this contact. Old-timers say it's not real ham radio. Yet it is exceedingly popular and out there everywhere. Now, I will say that there's an element, you're supposed to be by the computer when the computer is making these contacts and you have control. Some folks have hacked the software so that the computer actually is running all the time. So here's, Charlie Brown, how's FT8 working out for you, Snoopy? Well, my computer is working Asia right now. That's not what it was supposed to be, but okay. Here's some digital terms just to know, so that if people, are communicating at the ham club, you know what they're talking about. Bit error rate. You want a low bit error rate. You want error-free transmission of your digital data. A parity bit is extra data that's added to a header or a frame to use for error checking. A digipeater is a repeater used to relay digital communications using a mode called store and forward. Most TNCs have digipeaters built into them. Satellites above in low Earth orbit have digipeaters as well, so you can use packet radio to send and receive message via satellites. Node stations route data communications to other node stations. They could be on the internet, they could be linked by microwave. A phase shift keying, we talked about PSK31, but FT8 has just taken over from PSK31 completely. A radio message server, that's something you're going to use in the WinLink system. We talked about GPS, the global positioning system. COM ports are things on older computers that used RS-232 to connect serial data. A lot of ham radio gear still utilizes RS-232 serial connections. So a COM port is something that you need, or you need a USB to RS-232 converter, something like that. USB, Universal Serial Bus, that's what modern computers use. Gateway stations, they provide a connection to the internet for WinLink, for example. And the bulletin board systems, you'll still see them around, the old ones like I talked about before. All right, you didn't know that you were operating on a ham band right now and you don't even have your license. True. Wi-Fi. 2.4 gigahertz is a shared band. Ham radio operators know it as that 13-meter band. Or 13 centimeter bands, excuse me. And you can actually, with modified Wi-Fi routers like this Linksys, you can actually do long distance networking experiments. You can't use it for public internet connectivity, but you can use it to develop your own private mesh network for you and your buddies to be able to exchange data back and forth. This is Wi-Fi, also known as IEEE 802.11. It's a digital mode. That's the thing to know. Wi-Fi is a digital mode used by hams and by you. All right, let's answer some questions. So how are the transceiver audio input and output connected in a station configured to operate using FT8? And the clue is, what software do you need?
Bravo.
Yeah, you need the audio input and output from the computer, yep, and you need to be running software called WSJTX. Weak Signal Joe Taylor. Experimental. That's what it stands for. What signals are used in a computer radio interface for digital mode operation? Remember, there are three things.
Charlie.
Yeah, receive audio, transmit audio, and transmitter keying. And a lot of times now the interface is built right into the radio. So which of the following connections is made between a computer and a transceiver to use computer software when operating digital modes? If you're going to hack your radio, you got a goes in-a and a goes out-a. On the transceiver, the goes out-a would be the transceiver's speaker connector. The sound goes out-a the radio. And on the goes in-a is the computer's line input. That's where it goes in to the computer. So this is what you want. You want the output of the speaker connector going into the computer. That's one of those three signals that we need. So what is an amateur radio station that connects to other amateur radio stations to the internet? What's the term we use?
Charlie.
No.
Nope.
It's a logical name.
A.
Yeah, it's a gateway
gateway.
station that is connecting from the radio side to the internet, for example. And which of the following is a digital communications mode? Read carefully.
All of those.
Yes, packet radio, IEEE 802.11, which we learned is Wi-Fi, FT8, yeah, all of those are digital modes. And what kind of data can be transmitted by APRS?
A.
A is true,
Alpha.
alpha is true. Text messages could also be transmitted,
Delta.
and those
It's
text
delta.
messages could contain weather information from a weather station, so all of those, yes, all of those are possible. So which of the following is an application of APRS?
Alpha.
Yes, providing real-time tactical digital communications, that's the short message, in conjunction with a map, APRS.FI, showing the locations of the stations. So what does the term or the abbreviation PSK mean?
B.
Yes, phase shift keying. And which of the following is included in packet radio transmissions? Read carefully. My clue, read carefully.
Yeah, D.
D, all of those. And I didn't get specific, but packet radio, the header actually contains one of the first things you have to do if you get a new TNC is put your call sign in it. So it sends your call sign. So there's a checksum for error detection, a header that contains your call sign, and then the automatic repeat request in case of error. All of those are part of packet radio transmissions. And which of the following operating activities is supported by digital mode software in the WSJTX software suite? Read carefully.
Yo.
Delta is correct. Yeah, all of those things are supported by this one piece of software. You can do still the Earth-Moon-Earth transmissions. Bouncing signals off of the moon, or you can send up whisper signals and be heard by other stations around the world. It's called weak signal propagation reporting, whisper, and meteor scatter. That was another mode that Joe Taylor was interested in, bouncing signals off of the tails of meteors. So all of those signals are possible using WSJTX. So what is an ARQ transmission system?
Automatic repeat query.
Yeah. So which answer?
It's an error correct. Oh, it's Charlie.
Charlie, it's an error correction method in which the receiving station detects errors. Oh, I didn't get it. And sends a request for retransmit. Retransmit.
We use that a lot in GMDSS.
Okay, cool. So which of the following best describes an amateur radio mesh network?
Alpha.
That's where you use the 13 centimeter band of the 2.4 gigahertz Wi-Fi. You modify the router with software and boom, you got your own private network. So what is FT8?
Bravo.
Yeah, remember, it was a mode that we used during the time of the sunspot cycle where bands were dead, but it could hear things. It's a digital mode capable of low signal-to-noise operation. All right, section 5.4, power supplies and batteries. So some radios have built-in power supplies. In fact, some of the newer radios, 200-watt radios, for example, are coming with built-in AC power supplies. You just plug them into the wall. But a lot of equipment was built for use mobile, to be able to be used in a car or a boat or etc. And so they're 12-volt powered, where actually the nominal voltage you want is 13.8 volts DC for these radios. So you need a power supply to develop this 12-volt signal or 13.8 volt signal. And power supplies nowadays come in two flavors: conventional or switching power supplies, also known as analog. Conventional is known as analog, and switching are switch mode. The difference between them, both of them will generate DC. Here's an old analog type, and here's a newer switching or switch mode type. This thing is heavy. This thing has a big power transformer inside of it that weighs probably about 25 pounds. This thing is light as a feather. You can pick it up. It has transformers built into it, but the transformers are operating, instead of at 60 cycles, the transformers are operating at like 100 kilohertz. And that makes them much smaller, much lighter weight. And they both use regulated systems, regulators, to prevent voltage fluctuations, to keep the output right at 13.8 volts DC. So if you're going to be using a smaller mobile radio, like for VHF, UHF, you can get by with a power supply of 15 amps. That's a rule of thumb. If you're going to be using a 100-watt radio, like an HF radio, for example, you're going to need 30 amps, double that. So that's the dividing line. 50 amps for the smaller 50-watt mobile radios, and 30 amps for 100-watt HF radios, for example. Yeah, could be conventional, could be switching. And the good ones are, you can't really tell the difference anymore. It used to be the switching supplies were RF noisier. They generate interference. Not so much anymore. But learn from my mistake, all right? I needed a power supply, and I needed it to power my security cameras at my former residence. They come with those little power cubes. They're really RF noisy. They generate a lot of noise. And I thought, well, okay, I'm going to replace those really noisy power cubes with a 12-volt power supply, a 13.8-volt power supply. Okay, I was going to say hams are cheap, but honest, I'm cheap. I don't like to spend money when I don't have to. So I look on Amazon, and I see, oh, here's a Chinese power supply that has got a rating that looks good, 16 amps. Go over to the laptop if you would, Bruce. So here's the listing. So I bought this Audio Tech. It sounded kind of cool. 16 amp, mobile power supply, and I used it to power my security system and my security cameras at the former residence. It worked for about 2 weeks, and then it failed. And the transistors, the way that they failed, they probably overheated, and they failed shorted, so instead of outputting 13.8 volts, it output 21 volts DC and blew up all my cameras and all the other stuff. So if you're going to buy a power supply for your ham radio gear or whatever, buy a reputable brand. Astron, made in America, they're great. The Olinco one we saw there, but don't buy cheap Chinese power supplies like Gary did, because you'll regret it. You let the smoke out. Remember that? I let the smoke out. All right. Car batteries, well, there are all sorts of different kind of batteries now. It used to be that lead acid was it, the ones used in cars. the 13.8 volts comes from the nominal voltage when a vehicle is charging from the alternator. It's about 13.8 volts. When you turn off the engine, though, it goes back down to about 12.5 or so. Lead acid batteries, like the die-hard and whatnot you see, they charge from the vehicle alternator. This charging process, though, releases hydrogen gas. And that hydrogen gas must be vented out because hydrogen burns. Think of the Hindenburg. So you don't want that in a confined space. So keep that in mind, that charging and discharging can release hydrogen gas, especially charging too fast can release high levels. That's one thing to keep in mind with car batteries. Now, if you're running mobile and whatnot, you're going to have a rig in your car, and it's going to be an HF radio that is receiving single sideband. Oh, we said that single sideband is susceptible to noise pulses because it's amplitude modulated. You're hearing amplitude changes. You'll hear all sorts of noises in your car. Then you'll hear alternator whine, which is a that goes up and down as the engine speed goes up and down. You may hear spark plug popping, although most resistive cables and spark plugs have eliminated that. There's certain intermittent noises that'll pop up from grounding and bonding issues in modern vehicles. They're not all built on one chassis anymore. Improper radio connections can cause you problems. It used to be that you ran a 12-volt positive wire from the battery and you could connect anywhere on the car to get the negative return. That's not the case anymore. And we always say that you should run your power leads for your radio all the way back to the battery, both negative and positive. Better to connect all the way back to the battery because the other connections, number one, they may or may not be at ground potential, and number two, they're likely to be a cause of noise in a system that you don't want. Replaceable batteries. Remember flashlight batteries? Are you old enough? They're carbon zinc batteries. They're disposable. They're the cheapest kind. You can't hardly buy them anymore. They were replaced by alkaline batteries. Both of those two types, though, are not rechargeable. Now, nickel cadmium came along. They're rechargeable. That's great. And then other different types, nickel metal hydride, lithium ion, all of the various types that are rechargeable. So keep these in mind, what can be recharged and what cannot be recharged. And this is table 5-2 in your book. So some of the more modern batteries are amazing. Lithium iron phosphate batteries, like from BioNO and others. Remember the lead acid batteries were used to take 2 arms to carry the thing because they're so heavy. These things are lightweight, and yet they have a lot of power storage capacity. And the power storage capacity is measured in amp hours. So this is a 100 amp hour battery, and you can calculate the run time in minutes by knowing how many amps your device draws. Let's say it draws 10 amps, and this is 100 amp hours, so 100 divided by 10, you've got 10 hours of life from this battery. So these are wonderful, and so these are the future of batteries. There are all sorts of different battery technologies coming out now. It's wonderful that we have these storage options. We used our batteries a lot during Hurricane Helene to keep things going around here. We also used our small generator. I had a Generac generator that I used to charge the batteries and also keep the house going. And you can have just an old basic kind of rotary generator, which is what I have, or you can get inverter generators, have built-in AC inverters that smooth out the waveform coming out of the generator, keep it on frequency, on voltage, and in waveform shape proper. So these are questions and ideas you have to think about if you want to get a generator or an inverter. And the other thing you have to know is, well, how big? How much do I need? And you need to, if you're going to use it for your station, you need to think about, well, your RF output, how many watts output, okay, 100 watt radio, but it's probably only 50% efficient. So it's going to be drawing 200 watts when you're transmitting, and then you got other things that are going on. So is the generator or inverter big enough, the capacity in watts, for the things that you want to do? And then you have to consider also the wiring that you're going to be using, the ampacity. How much current can a wire carry? Well, larger diameter wire can carry a lot more current than smaller diameter wire. And what happens is you get voltage drop. The wire will actually start getting hot. It will be consuming power that you don't want it to be doing. Number one, it could cause you a fire hazard, but number two, the voltage at the other end is going to be lower than you want it. So the goal here is to get a large enough wire size so that you minimize any voltage drop when you're connecting up equipment. Oh, last questions. So which of the following is an appropriate power supply rating for a typical 50 watt output mobile transceiver?
Delta.
Yes, 13.8 volts at 12 amps. We say 15 amps, but 12 amps. Out of the choices here, that would be the one. Why are short, heavy gauge wires used for transceivers' DC power connections?
Alpha.
Yes, to minimize that dreaded voltage drop or loss of energy being converted to heat. And how can you determine the length of time that equipment can be powered from a battery?
Bravo.
Yeah, if you know the current draw of your equipment and you know the amp hour rating of the battery, then you can divide the amp hour rating by the current draw and get the time of operation. And where should the negative power return of a mobile transceiver be connected in a vehicle?
Alpha.
Yeah, we say back at the battery, at the chassis ground point, or even at the battery terminal. And which of the following battery chemistries is rechargeable?
Delta.
Yes, all of those can be recharged. And which of the following battery chemistries is not rechargeable?
Bravo.
Yeah, the old flashlight batteries, the carbon zincs. And what type of circuit controls the amount of voltage from a power supply? Or what circuit fails in the cheap Chinese power supplies? It is the regulator, the voltage regulator, the thing that is keeping 21 point something volts down to 13.8. That's what you want, the regulator. All right, what hazard is caused by charging or discharging a battery too quickly? Think Hindenburg.
Alpha.
Yes.
Alpha.
Outgassing of hydrogen or overheating. And that, ladies and gentlemen, is the end of Chapter 5. But I just want to introduce you to these websites, the ARRL exam review.appspot.com or hamstudy.org or qrz.com. You'll get these when you find the PDF in the Dropbox link. These are all places where you can start to take practice tests. Especially the ARRL exam review looks like this. And maybe next week I'll get a chance, I'll demonstrate this website to you. But you can use it to review test questions that we've talked about for the chapter, and also use it to take practice tests, because we're over halfway through the class. You're almost ready to take your test. Any questions, any final comments before we get out of here tonight? You've been great. This is what we call our class chat segment. Here, I wore you out. All right.
Yeah.
Well, I appreciate your attention tonight. Thank you, everybody, for your patience today, especially those watching on YouTube. My internet connection is back after Helene, but it's not right. And Charter, God bless those folks. And I know they've got problems everywhere. Their backbone links and whatever else are probably all messed up. So pray for them, pray for better connectivity, and hopefully next week things will be smooth as silk. We'll be back to normal. But I appreciate your patience. And as always, I say 73, and we'll see you next week.
Thanks, Gary.